The Universe in a Grain of Sand, Why We Study Atoms. Written by Neil deGrasse Tyson. Imagine holding the entire universe in your hand. It sounds impossible, doesn't it? But in a way, we do this every time we examine an atom. Atoms are the fundamental building blocks of everything we see, feel, and interact with. They are the smallest unit of an element that still retains the chemical properties of that element. Understanding the atom is key to unlocking the secrets of the universe, from the smallest particles to the largest stars. By studying atoms, we gain insights into the nature of matter, energy, and the forces that govern the cosmos. The journey to understand the atom has been a long and fascinating one, spanning millennia and involving the contributions of brilliant minds throughout history. From the philosophical musings of ancient Greece to the cutting-edge experiments of modern physics, each step has brought us closer to comprehending the intricate workings of the universe at its most fundamental level. Democritus, the first vision of the indivisible. Our journey begins in ancient Greece around 400 BC with a philosopher named Democritus. Democritus, along with his mentor Leucippus, proposed a radical idea. Matter is not infinitely divisible. They believed that if you were to keep cutting a piece of matter in half, you would eventually reach a point where you could cut no more. This smallest indivisible particle was what they called atomos, meaning uncuttable in Greek. Democritus's ideas were revolutionary for their time. They challenged the prevailing view, championed by Aristotle, that matter was continuous and made up of four elements: earth, air, fire, and water. While Democritus's theory was insightful, it lacked experimental evidence. It wouldn't be until centuries later that the idea of atoms would be revisited and placed on a firmer scientific footing. Nevertheless, Democritus's vision of the atom laid the groundwork for future scientific inquiry into the nature of matter. John Dalton, atoms as building blocks. Fast forward to the 19th century, a time of great scientific advancement. In 1808, an English chemist named John Dalton resurrected the atomic theory, this time with compelling evidence. Dalton's atomic theory, rooted in careful chemical observations and experiments, proposed that all matter is made of atoms, which are indivisible and indestructible. All atoms of a given element are identical in mass and properties. Compounds are formed by a combination of two or more different kinds of atoms. A chemical reaction is a rearrangement of atoms. Dalton's model, while simple, was a significant leap forward. He visualized atoms as tiny solid spheres like billiard balls, each element having its unique type of atom. This model helped explain fundamental chemical laws, such as the law of conservation of mass and the law of definite proportions. Dalton's work provided a solid framework for understanding chemical reactions and the behavior of matter. His atomic theory became a cornerstone of modern chemistry. J.J. Thompson, discovering the electron and the plum pudding. Dalton's model, while groundbreaking, would soon be refined as scientists delved deeper into the atom's mysteries. His model depicted atoms as solid, indivisible spheres, a concept that would soon be challenged. In 1897, British physicist J.J. Thomson conducted experiments with cathode ray tubes, which are sealed glass tubes with most of the air removed. These tubes allowed him to study the behavior of particles in a controlled environment. He applied a high voltage across two electrodes at either end of the tube, causing a beam of particles to flow from the negatively charged cathode to the positively charged anode. This beam was later identified as cathode rays. Thomson observed that these cathode rays were deflected by electric and magnetic fields. This deflection indicated that the rays were composed of charged particles. By carefully measuring the degree of deflection, he determined that these rays were composed of negatively charged particles much smaller than even the smallest atom. This was a groundbreaking revelation. He called these particles corpuscles, which were later renamed electrons. This discovery marked the identification of the first subatomic particle. This discovery shattered the notion of atoms as indivisible solid spheres. It opened up a new understanding of atomic structure. Thomson proposed a new model, the Plum pudding model, where negatively charged electrons were embedded within a positively charged soup, like plums scattered throughout a pudding. This was an attempt to explain the atom's overall neutrality. This model attempted to reconcile the atom's overall neutrality with the presence of negatively charged particles. Although later replaced, it was a crucial step in the evolution of atomic theory. Ernest Rutherford, Journey to the Heart of the Atom. The early 20th century witnessed a groundbreaking revolution in our understanding of the atom, thanks to the pioneering work of Ernest Rutherford. In 1911, Rutherford, a New Zealand-born physicist, conducted his now famous gold foil experiment, which would forever change the field of atomic physics. He fired a beam of alpha particles, which are positively charged particles much smaller than atoms, at a thin sheet of gold foil, expecting to observe predictable results. Based on J.J. Thomson's Plum pudding model, Rutherford expected the alpha particles to pass through the gold foil with minimal deflection, as the model suggested atoms were a diffuse cloud of positive charge. However, he observed something truly astonishing and unexpected. While most alpha particles did pass through the foil with little or no deflection, a small fraction were deflected at very large angles, which was completely surprising. Some even bounced straight back, which was an even more shocking result. These unexpected results led Rutherford to propose a revolutionary new model of the atom, challenging the existing theories of the time. He concluded that the atom must have a tiny, dense, positively charged nucleus at its center, where most of its mass is concentrated, fundamentally altering our understanding of atomic structure. The negatively charged electrons, he proposed, orbited this central nucleus at a distance, much like planets orbiting the sun, creating a new planetary model of the atom that laid the foundation for modern atomic theory. Niels Bohr, electrons in orbit, a quantum leap. Rutherford's model, while groundbreaking, still had some shortcomings. According to classical physics, electrons orbiting the nucleus should continuously emit electromagnetic radiation, lose energy, and spiral into the nucleus, causing the atom to collapse. In 1913, Danish physicist Niels Bohr addressed this problem by incorporating the principles of quantum mechanics into the atomic model. Bohr proposed that electrons could only occupy specific quantized energy levels or orbits around the nucleus. These energy levels were discrete and could not take on any value in between. Bohr further postulated that electrons could jump between these energy levels by absorbing or emitting photons of light with specific energies corresponding to the energy difference between the levels. This explained the unique line spectra observed when light from different elements was passed through a prism. While Bohr's model was a significant improvement over Rutherford's, it still had limitations. It worked well for hydrogen, the simplest atom, but failed to accurately predict the spectra of more complex atoms. Quantum mechanics, embracing the uncertain. By the 1920s, it became clear that a more radical departure from classical physics was needed to fully describe the behavior of atoms. This led to the development of quantum mechanics, a revolutionary theory that governs the behavior of matter and energy at the atomic and subatomic levels. Key figures in this revolution were physicists like Louis de Broglie, Werner Heisenberg, and Erwin Schrödinger. De Broglie proposed that electrons, previously thought of as particles, could also exhibit wave-like properties. This wave-particle duality challenged the classical view of particles and waves as distinct entities. Heisenberg's uncertainty principle stated that it was impossible to simultaneously know both the position and momentum of a particle like an electron with perfect accuracy. Schrödinger developed a mathematical equation that described the behavior of electrons in atoms as waves. Solutions to Schrödinger's equation gave rise to the concept of orbitals, which are regions around the nucleus where an electron is most likely to be found. The ever-evolving atom, a journey of discovery. The quantum mechanical model of the atom, unlike previous models, does not depict electrons following precise, defined paths around the nucleus. Instead, it offers a more complex and nuanced view. Instead, it provides a probabilistic description, where we can only talk about the probability of finding an electron in a particular region of space around the nucleus. This probabilistic nature is a fundamental shift from the deterministic views of classical physics. This model has been incredibly successful in explaining a wide range of atomic and molecular phenomena, from the simplest hydrogen atom to the most complex organic molecules. It forms the basis for our understanding of chemical bonding, spectroscopy, and countless other aspects of chemistry and physics. The insights gained from this model have revolutionized our approach to scientific research and technological innovation. The journey to understand the atom exemplifies the scientific process at its finest, a continuous refinement of our understanding through observation, experimentation, and the development of new theories. Each discovery builds upon the last, creating a rich tapestry of knowledge. From the philosophical musings of Democritus to the mind-bending concepts of quantum mechanics, each step has brought us closer to unraveling the mysteries of matter. The evolution of atomic theory is a testament to human curiosity and ingenuity. As we delve deeper into the quantum realm, we can expect even more surprising discoveries about the nature of atoms and the universe they comprise. The potential for new knowledge is boundless. The study of the atom is far from over. Each new experiment and observation opens up new questions and possibilities. New discoveries and technological advancements continue to push the boundaries of our knowledge, revealing even more fascinating aspects of these fundamental building blocks of our universe. The future of atomic research holds endless promise and potential.